welcome back. In this short lecture, I am going to take an example. So, this is an example on membrane osmometry, where osmotic pressures of aqueous solution of non-ionic surfactant dodecyl hexaoxyethylene monoether, which is the complex here, you can see the formula. It was measured at 25 degrees Celsius. Okay. At concentration below this 0.038 gram per liter, there was no osmotic pressure developed, indicating that the membrane permeation by the micellar species. So, remember that osmotic pressure means that certain will develop only when you have some specific one of the compound moves. For example, for the case of a solvent plus solute, if solute is also only diffusing, then there will be a osmotic pressure developed here, or vice versa. So, in this case, above this concentration, that is concentration 0.038, an osmotic pressure is measured, indicating the presence of impermeable aggregate species. So, the reason why they are showing aggregate species, because when you put ionic surfactant in a solution, they tend to also aggregate, but that aggregation depends on the concentration. So, what is saying that above this concentration an osmotic pressure is measured, indicating the presence of impermeable aggregate species. Okay. Whereas, below this the membrane permeation by the molecular micellar species, okay, which essentially means it was trying to have some kind of micelles like this, right, and it was kind of diffusing, it was allowed to permeate, and because the was permeating, then there was no specific pressure difference across it. But after a certain concentration, this aggregate, this becomes bigger, okay, and because of that there was impermeable aggregate species. So, only solvent was diffusing, but no species aggregate species were diffusing. Okay, there could be monomers and dimers and so forth, that is possible, they may diffuse, but this aggregate was not diffusing. Okay. So, would they measure this osmotic pressure, okay, for concentration greater than C0, and it was tabulated in this way. So, the question is to find out the second virial osmotic coefficient and the molecular weight of the species responsible for the osmotic pressure. It is a very practical examples you can think of, right, and determine the number of molecules in the aggregate, that is the second part. Assume they are spherical, estimate its molar volume and radius. Okay. I will try to solve some part of it and leave others you to ponder on certain other part. Now, what about the first part? First part is actually straightforward. If you look at the expression of the pi with respect to the concentration which we have written, we considered not much dilute solution. We wrote something like this: pi is equal to some concentration C, okay, RT 1 by M2 plus B star C and so forth. Okay. This was what we written. Now, what about the C here? C, considering that is concentration, is C minus C0, because this is the amount which we are talking about. So, this we are going to write it like this: C minus C0 is equal to RT by M2 plus RTB star C minus C0. Okay, I am not interested in the higher order terms. So, if we plot pi by C minus C0, okay, versus C minus C0, then I should be able to calculate. So, if I use pi by C minus C0, okay, then I should be able to get some data point. Okay, and this turns out to be linear. Okay, so without scaling anything, I do not want to draw a scale here, but the idea is you have to use this data which is shown here given to us. So, this data is available, right. So, you write here pi by c minus c 0 and get the data. So, you can plot this versus this, okay. And if you get that, then you should be able to obtain the intercept, okay. So, you use least square fitting in this such a case. So, if you do that, you get intercept which turns out to be 199.28 Pascal liter gram per gram. You have to convert into the units well, okay, because this is an important part of calculation. Okay. Now, I know R, I know T, so I can get M2. M2 turns out to be, because this is a 25 degree Celsius experiment, now I can comfortably write 199.28 because everything in SI unit, and this is nothing but 12.439 kg per mole, okay. Or you can write as gram per mole also, which is going to be 12.439 gram per mole. Now, what about the slope? Slope is 0.727, which is nothing but RT B star. So, I have now B as 2.93 into 10 to the power minus 7 liter mole gram square per gram square. B2 is a coefficient which provides you the idea about the interactions, whether interactions are effectively attractive or repulsive. So, now you have data, you have calculated your molecular weight. Now, the question is, what is the number of molecules in the aggregate? That is the question. Now, let us look at this. Okay. So, this is the non-ionic surfactant for a monomer. What is the molecular weight of this? This will turn out to be 390 gram per mole. Okay, 390 gram per mole. And what is the value we got for M2? 12439. So, certainly is an aggregate. Okay. So, we can simply divide it. So, 12439 divided by 390 is 32. So, this is the aggregate in the molecule, but what about the other part of the question, which is, if you assume this aggregate to be spherical, estimate its molar volume and radius. Now, this is a bit tricky because this is something which you need to connect B star to V. How are you going to do that? So, apparently, without going into details, I would like you guys to take a look at the book, which is Principles of Colloids and Surface Chemistry. So, here in this book, the B is well connected or is related to the excluded volume, okay, through this relation. Okay, this is the excluded volume, and from there we can obtain the using this spherical nature of the aggregate to obtain the volume. Okay. So, you need to know how to get use of this this excluded volume concept, but I would like you to look into this if you are interested to obtain this. Okay. All right. So, with this I can now move on to another topic, which will be very short again. So, I will just talk about solubility of solids, and I wanted to talk about the liquids as well, but since we have not discussed much Henry's law, so I will defer this aspect once we cover the liquid mixtures part. So, I will just talk about only the solids in compressed gases. Okay. For the case of the gas at low pressure, we can take the vapor pressure or vapor phase fugacity as simply 1, right. But the vapor phase fugacity becomes an important parameter when you consider, let us say, solubility, okay, of solid or high boiling liquid. That means they are very dense for particularly the dense gases. So, if the gas is dense, you have to understand how to get the fugacity coefficient of the gas phase. So, that means that for dense gas, it is important to include correction terms, right. That means the fugacity coefficient, which will capture the non-ideality. So, let me describe the system to appreciate this. Consider equilibrium between a compressed gas and solid. Okay. Now, so we are talking about a compressed gas and a solid, and solid will not have any diffusion of the gas. So, we assume that basically the solubility of gas in solid is negligible, 0. Okay. And thus, which means basically solid is pure, right. So, we consider gas as 1 and solid as 2. So, at equilibrium, let us say for 2 for solid, f of 2 s is f of 2 v, okay, which means basically the fugacity of a solid component in the solid phase should be same as the fugacity of the solid component in the vapor phase. That is what we are talking about. Okay. Now, since F2S is a pure, we can straight away connect this F2S as P2S phi 2S exponential P2S P V2S by RT Tp, right. This we can write, and this is nothing but the saturation vapor of the pure solid, right, because we are talking about solid, and this is at saturation pressure, right. Okay. And for the vapor phase, we can simply write the standard expression that F2 V is phi 2 Y 2 P. I have this relation and I can make use of this. So, this is 1, let us say 2 and 3, using 2 and 3 plugging into 1, I can write as Y 2 here as P 2 S by P and some factor E, okay, where E contains everything. E contains phi 2 S by phi 2 exponential P 2 S P V 2 S by R T. Okay. So, this is what it is. So, Y 2 is nothing but the solubility of the solid phase in the vapor, right, that is the composition or mole fraction. Okay. So, now we can just talk about what is E. E is nothing but the enhancement factor. Okay. So, when E is 1, when P approaches to P2S, okay, when P approaches to P2S, basically E approaches to this. So, E is greater than or equal to 1. In fact, many times for many cases E is much larger than 1. So, what are the components of E? If you look at E contains Poynting factor, phi 2s, phi 2, 3 parameter, right. So, which one is the most important parameter? What is the phi 2s represent? Non-ideality of the pure saturated vapor, okay. And Poynting correction, of course, we all know that pressure effect. What is phi 2? This is the vapor phase fugacity coefficient in the high pressure gas mixture, right. Because it is dense, so pressure will be very high. It is not a low pressure system at all. And this is the one which plays a bigger role. The Poynting correction will contribute to some number like 2 and 3 to E. Phi 2 is typically small, so phi 2 will be close to 1, okay, but phi 2s will be close to 1. But what about phi 2? Phi 2 will be much less than 1, which essentially means, because phi 2 is here, right, that E will increase, okay, sometimes to 10 to the power 3 or more. So, Poynting correction will give you 2 to 3 numbers like times, and because of this phi 2, it is important that we calculate it very well. So, E will tend out to be typically in the range of 10 to the power 4 to 10 to the power 6, which are common, but you can also have 10 to the power 12, that large number, and this is the case, for example, in the case of solid oxygen in dense hydrogen, okay, very specific case, but this is a common molecular system. So, E is the enhancement factor which plays an extremely important role in the solubility of solids in gases, okay. Okay. So, let me show you that how do we actually make use of equation of state, okay, by a few examples. So, this is the E in a logarithmic scale, and for the case of solid CCl4 in supercritical CF4 at this temperature, and as you increase the molar density, make it more denser, pressure is more, the enhancement factor increases, okay. It is in the logarithmic scale, and you can clearly see that this equation of state was well captured, could capture the behavior very well and is in line with the experiments, okay. Now, here this is the solubility of solid CO2 in air, okay, at 143 Kelvin. This is a mole fraction of CO2, the solubility, that is what you talk Y2 as a function of pressure, and the symbols are the experimental data. If you had used only the ideal gas, it could capture only very little amount, very low pressure. If you use only the second virial coefficient, that if you are using the equation of state with only second virial coefficient, then it can capture again up till certain pressure, which is up till 40 bar. So, but for higher pressure, you need to also add the third coefficient in order to get the right equation of state. So, virial coefficient has its own issues, okay. If you want a correct equation of state, there are other equation of state, but such as Peng-Robinson, these are the equation of state which is well developed. But virial coefficient, there is a possibility if you increase the density of this, you may also need another term, the fourth virial coefficient also. But apparently for this condition, third virial coefficient works very well, okay, for this region, where if you had used only the second virial coefficient, it fails to capture the high pressure domain, okay. In addition, you can also see a very unusual cases such as the maximum and low minimum in the solubilities. So, this is the case of naphthalene in compressed ethylene, okay, at different temperature, and this is a mole fraction again Y2, in a Weber phase pressure, and the virial equation state in this case does not work. If you had used this, it will fail. So, the data is again here, you can see this is here, the data are limited, but if you had used Pang-Robinson equation of state, then it captures this as well as shows that there is a maximum and there is a minimum solubility which depends on the pressure. So, having also fitted this, you can also predict this kind of thing using basically the equation of state, which is this one. So, remember that this we do not have the data experimental data. So, this is like obtaining this information right from the equation of state, where this captures the intermediate pressure range. All right. So, I hope that it gives you an idea how this has played an important role in thermodynamics, molecular thermodynamics in particular. And in the next lecture we will start fugacity of liquid mixtures. So, hopefully you will get to learn little more about liquid phase and as well as the utility of activity coefficients, and I will also talk about the Henry's law. So, I will see you in the next lecture.